Does it show up?
Yeah.
Shall I increase the font size a bit?
Maybe yes.
More? Little more? It's all right. Back side. You can see? Yeah. Okay. Fine. So, right. So very simple. This is what I'm going to use, and I just defined some parameters. So whenever I'm going to okay, I haven't talked about it. How are you going to store an implicit function? You have to sample it, right? If I'm going to show it on a computer, I have to capture it, I have to sample it, and then I show you. So implicits are almost always sampled. They are like a signal, you could say. Okay, I have to sample it, and it's a bivariate. Circle is a bivariate implicit. So this is going to be what's the best representation I can use for that? I can use an image. Okay, so I can have a grid of implicit values I could sample. So this is how I do it. Okay, so I take a grid, and that's my grid over here. That's my grid, and what I'm saying is that, let's say this is my circle here that I want to represent, the implicit of this, right? Remember, the implicit is going to take xy values and output a single value, scalar value, right? So I am going to sample it. The simplest sampling I do is over a grid, right? So this is a grid, a regular grid, so to say. It's a regular grid, and as is the case with any regular grid, the sampling happens at the center of the grid, because the grid has a finite dimension. Okay, this has a finite dimension, right? I mean, this is going to be some delta x, and this is going to be some delta y. In fact, your pixels, the sensor that is in the camera has some dimensions in millimeters, and if you go check out specs, you will find the sensor has some finite size. It has to, right? It's a physical device, it's a physical thing. So every pixel has a very, very tiny size. It's not zero. It's not just a zero-dimensional entity. It has some finite size. So it's a rectangle, more close to a square, but it's a rectangle. But if it's a rectangle, where exactly do you store the value? At the center of the rectangle. Okay, so you store values at the centers. In a grid, you can call it a pixel grid or just a grid. Grid is good enough. The values are stored at the center, right? But that's not sufficient. We need to attach a coordinate system before we can assign any xy value to these points. So as it is typical in images, the x-axis runs like this. Unfortunately, the y-axis runs like this. Do you know that? Yes, y-axis runs down, right? In your computer screen, if you go, I don't know, there must be some tools. You can get the mouse coordinate. 0, 0 is top left, not bottom left, okay? Which is somewhat opposite to what we are used to, but that is how it is. But that's not a worry. I mean, we just need to flip our notion of y-axis and we are done, okay? And this is your height, and this is your width of the image or grid. Okay, so now we have a coordinate system attached, and for clarity, let me put this x up here. Too much. Okay, so this is x, and then now it's fine, I think, right? And this is a regular grid. Okay, so I have a coordinate system attached, I have size of every pixel, and I know that at the center I'm going to sample this implicit function. So I just need to enumerate the coordinates of the centers of all the pixels, let's say, right? So typically what do I do is that I say that the first coordinate here is 0, 0, and then this one is 1, 0, and so on and so forth. This guy is 0, 1, da 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 da. Okay. Now you might wonder, okay, center of the pixels are integer coordinates. How about the corner of the pixel? Who can tell me the coordinate of this guy? What is the coordinate of this guy? Come on, fast. Minus 0.5 comma minus 0.5. Right, good. So that's assuming that delta x equals to 1, delta y equals to 1. Okay, right. But that's fine. I think for now that's fine. So let me just erase this delta x here, and just, it is understood that it is 1 units. But you know the drill. If it is not 1 unit, you're gonna you have to multiply with the size of the pixel. Okay. Anyway, but we are just interested in the center, so that's good enough. So I do the same here. I say the width is 100. You can see, right? The width is 100 equals to x square plus y square minus r square, and this is a paraboloid. This is a paraboloid. The cross sections are circles, right? The xy cross sections are circles, but if you slice it in yz or xz, then you will get parabolas, right? And that's a paraboloid. It's a surface of revolution. Okay, revolution of what? A parabola. Okay, so it's a paraboloid. Good, good. All right. So that's my this thing, and so yes. So now that we are discussing this paraboloid, interesting point. So observation. So we have this. Let me try drawing this paraboloid. This is going to be something like this. Okay. The level sets are nothing but cross sections of an implicit. So that's my level set. So the level set at z equals to 0 is my 0th level set, right? It's just saying the same thing in different words, but now that you know that the function f for a circle is a paraboloid, then I thought I would just draw and show you that, because we just discussed that the cross sections along z are all circles. That means all of the level sets of this function are circles. Okay, right? Clear to all? All right, good. So any questions on implicits? No, what do you mean? A paraboloid is just this much.
Yeah, you draw it like this, but in the diagram that appeared
Oh, really? No, I don't think so. Was it? There are 2 lobes. I don't see 2 lobes. I just see 1 lobe. This is just 1. Where do you see 2? Come again? Is it 2? Is it showing up as, that's the displayed, it's too bright. It's too bright. What do I do? This is too bright. Can I rotate for you, and then do you see this now? Is it possible to reduce brightness here? That's why he sees two lobes, which is not really the case. So everything is brightened up on this screen, then it's not good. Is there a brightness thing here? Or maybe we can't turn off the lights, yeah. But then the board will be black.
for a few minutes. I'll turn it on.
Yeah, you can just turn it off, all off at once, and then Okay, is it better now? Don't know. Even now you see, so it's just like a tent, like a cloth, and then it's just, even though the tent per se is not really a paraboloid, right, Kaushik? A tent is not a paraboloid. No, it's just one side, but it's been, I think it's just the way it is plotted as. So these four are like four corners of a cloth, and then it's just hanging, right? So, but there is just one minima here. There is just, there's a single lobe here. This guy has not brought this pointer. Maybe we should. Could you just remind him to get the pointer? He said he will, but right. So I thought if I rotate, you would get a sense of what is happening. So just see that. Just see the rotation. Just see the rotation. Does it look like a single lobe or two lobes?
From one complete side it's looking like single, but
Okay. We can. I can share these things, and then or maybe this diagram also, and it will make more sense. Right. So this is what happens. A sampling is just a small view of what is happening. Right. So what I'm showing you is I'm cutting this parabola in a box. So I'm cutting this parabola in a box like this, and I'm showing this box to you. This much is what I'm showing to you, and that's why it looks like that. Okay, but yeah, you can take a look at it later also. Maybe on a computer screen it's gonna look better. So one thing good with MATLAB is I can save these figures and share, and then if you have MATLAB, you can, or Octave, you can also use Octave, which is an open source software. Open it up, and then you could rotate around the 3D plots. So I think that let me do that, and then you could go back and verify that it's indeed just one lobe. It has to be, it's a paraboloid. Okay, so all right, just close these windows, right? Okay. Yeah. Okay, so a little bit about continuity and gradient. You would want to make sure that there is no jump in the function. If you have C0 continuity, that makes sure that, I think we can turn on the lights. I think, thanks Kaushik. So a C0 continuity ensures that the function is continuous. Okay, what do you mean by continuity? Is that there are no gaps in it. So if I have a function like this, not a smooth function, there is a it's not smooth here, but it is continuous. Okay, it is continuous. So this is known as C0 continuity. You covered it yesterday or day before yesterday, right? So C0 continuity. So if f is C0 continuous, its derivative will be discontinuous. Okay, so for a 3D scalar field, that's going to be the gradient. Okay, the gradient is all the partial derivatives. It's a vector of all the partial derivatives of the function. And now if the gradient is C0 for each component, that means that the function was C1 in the first place. That is why the gradient was C0. Okay, so just a few things you want to make sure, right, is C0 for a function is not good because the derivative is not defined. Is the normal vector here, or here? You don't know, right? So if you at least have a C1 function that is differentiable at least once, then you know that its derivative would be at least continuous, if not differentiable. Okay, because if the derivative is discontinuous, the gradient is discontinuous, you cannot define tangents or normals at that point. It would be difficult. There are many choices in that case. Right. Any question about implicits before we move further? Okay, good. Anybody? Questions? Yes? No? All right, good. Okay, so now let's take a look at some specialized implicits, and this one is known as a distance field. It's a field, it's an implicit field. So again, it takes xy values or R2 in R2, or it could be a 3D distance fields. In that case, our point in R3, and it gives what? A scalar value. Okay, it's just, everything is same, it's just an implicit, okay, just a special type of implicit, and it's called a distance field for a good reason, is because the value that it stores is a distance from somewhere. Okay, so let me give you an intuition as to what it is doing, and then I think all of this will follow. So don't read any equations yet. What you could do is, if I define a shape, let's say some shape, okay, some weird shape, and then, or maybe I want to define a simple shape, because this might be confusing. So let me draw a rectangle. Okay, now I'm inside here at point P at a coordinate x comma y. I want to define this distance field for this rectangle, and distance field are going to store distances, right? What type of distances? So if this is my rectangle R, its boundary is denoted as partial of R. Okay, when you read partial R, that means the boundary of the shape. So do I have some other color here? So let me just put this in red. That's the boundary of the rectangle, okay, partial R. So the distance field is going to store distances, shortest distances from this boundary, not just any distance, shortest distance. So distance field FIELD is going to store shortest distance to the boundary. Okay, so what will be the shortest distance from P to the boundary? What should I do? Perpendicular. Okay, there are 4 perpendiculars here. Which perpendicular? The least one. Okay, what are the candidates? I have this, then I have this, and this, and I figure out, okay, which one should I pick? Turns out this is the shortest one. So this, whatever distance is this, the distance field is going to be d of P equals to, or let me not call d is like abuse of notation, let me call df. df at P equals to this d, dxy, whatever it is. Okay. I could have also checked for all the distances, right? I could have said, okay, I can measure distance here, 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 all the points on the shape and pick the minimum. But why did you say perpendicular? Why should the perpendicular give the minimum? Okay, let me give you a slightly difficult shape, and then you tell me, can you have a perpendicular or not? Let me say if this is my shape and I have a point P here. Now tell me what would be the distance. Perpendicular again? Perpendicular to the tangent. Tangent at what? At any point on the boundary, right? Perpendicular at any point on the boundary. So I take a point, and let me call it Q. There's going to be a tangent. At any point I can define a tangent, right? Any point is going to be a tangent. And because there is going to be a tangent, there is also going to be a normal vector, just for your knowledge, okay? The normal vector is like this, perpendicular to the tangent. Anyway, don't bother about normals as of now. But it so happens is that, you know, for simplicity's sake, I could just compute distances from all points on the boundary and pick the minimum, right? And that's going to land me up somewhere here. You guys can see it's going to land me up somewhere here, let's say, right? It so happens that this perpendicular, sorry, this segment is perpendicular to the tangent at that point. So the minima comes out to be perpendicular to the surface, right? we'll do something on it if time permits. And as a result, this is also the normal vector. It's the same direction as the normal vector to the boundary. Are you able to? Is it okay? Please ask questions if this is right. It turns out, that's it happens so. Okay. Now, but if you have this is for smooth surfaces. If you don't have smooth surfaces, then things are not so easy, because then you have corners. And then again, you can't define tangents or normal vectors. In that case, everything goes for a toss. All of this thing will go for a toss. But you could still go back to the first definition, that just select all the points, take the minima, and done. You can still define your distance field by just going through all the points and computing the minimum distance. So that's my distance field at every point. So again, it's a field, right? How many distance values will you compute to capture this shape? So you sample. You see, you have to sample. Just like we sampled an implicit function, you sample a distance field. For that, you must have points at which you want to evaluate the distance field, right? So let's say you have tons of points here. For every point, you can calculate the distance values, and that's your distance, your your sampled distance field. Okay. Many times we do two types of sampling. We could do sampling on a on a mesh, a triangle mesh or a polygonal mesh, or we could just do it, just we did in the previous case, do it on a grid. Okay. So both ways are perfectly correct. Okay. You could sample on an image or a grid, regular grid, or on a triangle mesh, and you can do pretty much all the stuff with that. Okay. So right. So coming back here, now does this definition make sense? That a distance field is defined with respect to some geometric object T. In our case, the geometric object was the boundary of the given object. Okay. So f of T comma P is min over all points Q belonging to T. So you take all points Q on the boundary T and calculate Q minus P, distance between Q and P, which is Q minus P mod here, right? This is okay, the definition. Sorry. So right, need not be Euclidean distance. Now, a distance field is usually computed with distance with Euclidean distance, but you could use some other distance as well. You could use Manhattan distance, or any distance that you have with you, and that would be that particular type of distance field. It may have different properties, but Euclidean distance field have some special properties which make them so special, right? By the way, distance fields are used in a lot of fields, right? Robotics, anybody from robotics here, right? So robotic navigation, they use a lot of distance fields, right? So questions on distance fields? Okay, no question? Maybe a demo will be good, and I have an interesting demo. Not interesting, I think the image is interesting. So right, now it so turns out that there is an associated partial differential equation known as the Eikenal equation that you can solve to get a distance field. Again, this is just too bright, I believe, so all the images look a bit weird here, but I hope you could still make out something. So if you look at this equation, so the magnitude of the gradient, how do you read this equation? The magnitude of the gradient is 1. The magnitude of the gradient is 1, full stop. Magnitude of the gradient is 1. Could somebody tell me what it conveys? So for a distance field, it's a property, let me finish. For a distance field, it's a property that the magnitude of the gradient is exactly 1, if using Euclidean distance. And that's exactly what the PDE says. Grad f magnitude equals to 1. What does it mean? Could somebody elaborate? Anybody understood that? Yeah, go ahead.
Make the plane, tangent plane at that point of the curve, then it will make.
Okay, wait, hang on. Terminology. Tangent plane is for a surface. For a curve, it's just a tangent. What do you mean by tangent? Okay, just for your clarification, if you have a surface, you're going to have a point here. At this point, how many tangents can you define? You can define infinite tangents, because at that point, all of these are tangents, right? You could just keep on enumerating tangents. So you say that at this point, you don't have single tangent, but rather you have a tangent plane. Okay, so this is a tangent plane. This is a tangent plane, right? And any vector on this plane is a tangent to this surface at that point. Okay, so that is called a tangent plane. Let's call it T, right? And there is one normal vector here, which is perpendicular to this tangent plane. For curves, you just say tangent, right? For a curve, at any point, you just have a tangent, right? There's a unique tangent here, right? So I think you wanted to say tangent. Yes, please now go ahead.
The normal vector for the tangent plane will make 45 degree with the xy plane.
Oh, come again.
The normal vector
Hmm.
will make 45 degree with the xy plane. They are in 3D.
In 3D.
Yeah, so the xy
The norm. Sorry. Okay. Even I have to decipher. Go ahead.
the normal vector or the plane, some either of the one will make 45 degree with the xy plane. Yeah,
Gradient with respect to what? Hmm. Gradient is with respect to its variables, right? The partial derivatives. Pointer. So T is what is T? I think we are no. Okay, let me just erase this. T is confusing. Okay, this is not right. So T is fixed. Yeah, T is fixed. T is the boundary. T is the boundary of my shape. So yes, with respect to x and y, those are my variables here. So my gradient is del f by del x comma del f by del y. That's my gradient. Okay, and maybe shall I show you the 3D plot first, and then we can come back to this question. Sorry? Normal to the gradient will what? Yes, tangent is normal to the gradient. Of course it is. It is. But what about that? Okay, let's look at this plot first, and I think maybe we can just answer it on the plot itself. So where is my dt? Yes, wonderful. Okay. Okay. So I have this image of the silhouette of Indian map, and you can see it clearly. Okay, great. So that's the shape, and I'm going to compute distance field on it. Okay. And it's interesting because it's the Indian subcontinent, and then it's a very irregular shape. It's not like a circle or a rectangle, right? So we are going to see some interesting distance field on it. So now so happens in MATLAB has one single function to calculate the distance field. In this case, what you do is that for every point inside the shape, you just enumerate, you just calculate distances from all the boundary points, pick the minimum and store the distance, right? So, if you were to implement it yourself, you are going to first figure out the boundary, enumerate all, store all the boundary points in a list, right? For all the grid points, calculate distance to all the points in the list, take a minima, and then store that distance at that grid point pixel. Okay, clear, right? That would be the algorithm. It is time consuming. What is the complexity of this? For an image, for a 2D case, what is the complexity of calculating distance field? If n is n by n is the image size, and let's say my list of points is k n square, it's of the order k n square, so it is expensive, right? Computing distance field naively is expensive. Okay, anyway, so but MATLAB does it for me, so I don't really bother myself too much. And then let me just run these two. Okay, so that's my, oh wait, typing. Okay, now it's good. Right, so I have just calculated the distance field inside, and again I'll just maybe turn off lights here. This is okay. I mean, it's oversaturated here, but you could still make out what's going on here, right? The distances increase from the boundary toward inside, and you have some maxima at the near the center, right? In Madhya Pradesh, you have the maxima. Who is from Madhya Pradesh here? Anybody from Nobody from Madhya Pradesh? No? Okay. So you have the maxima here. Okay. So you can't see too much of the slopes and normals and gradients here, but let us just plot in 3D and see what happens. So again, use the same function, and now this, okay, see if I can align it. Oh, this is needs some rotating, but right, okay. Okay, now let's stay with this image for some time, and you see these mountain-like structures. Now, does it change your understanding of Eikenal equation? Let me write Eikenal equation again here. So, what does the Eikenal equation say? Is that the gradient of f, the magnitude of that is equal to 1 everywhere. So, I could say that everywhere on this map inside, the magnitude of the gradient is exactly equal to 1. Does it look like? Now the consequence is, if I were to take my car and ride, the maximum slope I will encounter is 45 degrees, not more than, it will never be 60 degrees or anything above 45. It could maximum be 45 degrees. That's still steep. I don't know, can't drive on 30 degrees, so 45 is steep. But that's the max you will get, no more than that, right? But is it evident from this 3D plot?
So you said we want the maximum of 10 meters.
It could be 30, it could be,
It's just one. That's
but when you want to measure slope, okay, let's say this is part of a mountain. How are you going to measure slope? Are you going to measure slope in this direction, or this, or this, or this? There are 360 directions to measure slope along. If I measure slope along the horizontal, it is exactly 0. I could construct a road that goes around the mountain, doesn't take me anywhere other than just taking a trip around. It doesn't go up or down, and that road is going to have a slope of 0, right? Or I could have a slope downward that takes you back to Delhi, for example. You're coming back from Shimla or somewhere, it takes you back. If you up the road slope, by the way, the slopes on these roads are usually kept fixed, so they try as much. Okay, so these roads on mountains usually have fixed slope, so that the rider, the car, doesn't experience, ups and downs too much, but you still have that. But along a stretch, the slope would usually be constant, right? The consequence of keeping constant slope and a low slope is that the road will become very long. If you keep the slope high, then you have a shorter trip, but it's going to be tiresome. Okay. What this says is that the maximum slope is going to be along the gradient, and that is going to be exactly 1 always for a distance field. That's the maximum slope along, and that will happen only along the gradient, only along the gradient. Okay. Was that your intuition as well? Okay. Anybody wants to discuss it a little more? Think about it, okay, and come back to me. Maybe afternoon also we can discuss that. But that's what the Eichner equation says. Okay. Now, in 2D, it's a bit difficult to imagine that the slope would be 45 degrees. But I can clearly draw it in 1D, and then you say, yes, the slope is 45 degrees. Shall we do that very quickly? So let's draw a one-dimensional 1D distance field. So how is it going to look like? So you have okay. So you need a boundary, and one-dimensional boundary is going to be points, right? So let me say these are my axes, y, x, and let's say I have, for sake of simplicity, I have 2 points, P0 and P1. Okay, and I'm going to construct distance field throughout, and y-axis measures my distance field value, and x-axis is just this points. Okay, so who will tell me how it's going to look like? At P, what would be the value of the distance field? Louder. 0. Okay, at P1, 0, again 0, and remember it's going to measure distance. So how should it increase? So the increase here, so the increase in x is going exactly be the same as the increase in y, because I'm just measuring distances, right? How far is, if this is 1 unit here, you know, some value P2 is 1 unit, its distance value is going to be 1 unit. Okay, so you're going to have a point here which is 1 unit here. This is 1 unit, right? Clear to all? Okay, so I'm going to erase this one quickly, and then I want one of you to come down here and draw the distance field for me. Who wants to come and draw a distance field? Somebody who is in doubts about distance fields should come, and I'll help you. I'll help you make sure it is good. Come on. The point I'm going to explain, but first I want you to. What's the? P could be any point. Sorry? So this is x-axis, right? This is, let's say this is origin, and P be some, let's call it x0 and x1, if that is easy. Oh, yeah, T is this. So T is the set x0, x1. It's just 2 points, right? I mean, in 2D case, you have some shape boundary, right? That's my T. Every point on this boundary. In this case, 1D case, I have 2 points lying on the x-axis. That's my boundary. Let's say, okay. With respect to that, I want to compute. Aajo, tumi aajo. So use the understanding of distance fields and try draw. Remember, there are 2 of these, so something weird is going to happen in between.
Okay, so we're going to do this
for the entire real line, the x-axis. Okay, and it's a distance field, so distances are always positive. Euclidean distance. Okay, go ahead, please.
Okay, so for something over here,
Mm-hmm. So a unit distance along x-axis is going to give me a unit value, right?
so that's why you put this.
That's why I put this, but it's not really. Yeah, this is fine actually. This is fine. So you could just keep going along that one, and then in both directions, also left of x.
That's
Hmm.
what.
Hmm.
So then you do so this 2,
Hmm.
right? So you need 2 over
Hmm. No, that's root 2, but that's root 2. That length is root 2.
here. Okay, so this
The y value is 1, the length itself is root 2. So do not have to write it. This is okay. I mean, what you could do is, this is 1, which I have already written here, so you could write 2 here. Yeah, exactly.
so what I understand reach the point of
It's gonna reach a peak.
Huh?
It's gonna reach a peak.
then it goes down.
Then it will go down. Very good, wonderful. So just draw it. Then it goes down, and there's a peak. And to the right of x1, what happens?
So
Another mountain.
we keep going.
It will keep on going, right? There's nobody stopping it there. So dot dot dot. Same happens here. So draw it. Okay, very good. Thank you so much. Please take your seat. Okay, so that's how the distance field is going to look like in 1 dimensions. I'll just redraw it slightly for just a bit of clarity here. So yeah, something like this. Where would the maxima be? Midpoint, exactly the midpoint. So x0 plus x1 by 2, and that's where it's going to reach the max. And yeah, by the way, what would be this value?
1 minus x naught by
What?
x1 minus x naught by
X. Here's a point. This is this distance divided by 2. What that would be? x1 minus x0 divided by 2. Is that correct? Yeah. Now tell me, do you see the slope? 45 degree. Right? How many of you don't see the slope yet? Raise hands. How many of you do see the slope? 45 degree slope? No, not because I drew it in 45 degrees, but I could have drawn it something like this, and then it's certainly not 45 degrees. But those who have raised the hand, why is it 45 degrees?
when distance Euclidean distance in one direction, so the increasing df will be the same as
The rise is equal to run. Rise as in rise, going up is equal to how much you are running. Obviously, it's going to make this slope of 45 degrees. So you go d units along this x-axis, and then you have rise in d units along the y-axis. What is the angle? This is exactly 45 degrees, right? And this is true in all dimensions for distance fields. Albeit, the only catch is that it has to be measured along the gradient. This is true only along the gradient direction. If you are not along the gradient direction, this won't happen. Okay. So you do gradient ascent or gradient descent, you're going to encounter a slope of 1. I think enough on this slope. Let's move ahead. Okay. Okay. I hope everybody has an idea about that now. Okay. Right. Let me see. Okay. Let's come back to this one. Okay. So that was about distance fields, and now there is a very useful variant of distance fields known as the signed distance field. So we break at 11:30.
11 to 11.
Oh, break is 11 to 11:30. Okay, okay. we can do that in 5 minutes. We'll break. Yeah, I'll just cover signed and then we can take a tea break. Right. So the signed distance field is a variant of distance field which is very simple. It says inside values are negative, outside values are positive, or vice versa, depending on what is convenient to you. You could say inside positive, outside negative, full stop. Nothing more than that. Okay. And when you assign a sign to the distances, it is known as assigned distance field. Okay. Why is it necessary? It is useful because now the distance field is this implicit that has a 0 level set. Why? Because it has values going negative, it has values going negative, it has values going positive, and there's going to be a 0 level set which is exactly the shape's boundary. Okay, you want to see that? Maybe a quick demo? And then we could completely skip these equations because there's nothing much there, but I think a demo is needed. Okay.